Hello everyone and welcome to my class, General Chemistry 101, and today we are going to start chapter 8, which is periodic relationships among the elements, and we are going to talk about in this chapter more about the periodic table and its properties. So one can wonder why the periodic table has been arranged this way. Like, this is a question, why the periodic table looks like this. Actually, there are different forms of the periodic table. This is just one of them. And if you look at the internet, you will see different versions of the periodic table or different forms of the periodic table. But you need to notice first that not all elements has been discovered at the same time. Some of these elements, we know them even from the old ages, like carbon, nitrogen, oxygen. We know these long time ago, iron. But some of these elements they have been discovered recently, and this is the modern view of the periodic table. You will have some old versions of the periodic table that looks actually different. And the reason of that, because first of all, people were arranging the periodic table according to the mass number, to the atomic masses of the elements. But they have figured out that this only works towards calcium. After that, the periodic table will look weird. Then Mendeleev and Mayer came up in the 1869 years, in the year 1869, and they figured out a way to arrange the periodic table according to the atomic number rather than the atomic mass. And the present periodic table is actually based on Mendeleev's idea. Now, the modern periodic table contains four major groups of elements or major classifications. The first one is called representative elements, or what we call the main group elements. We have also the noble gases, which basically they don't react with something, but they discovered recently they do react. Some of them they do make compounds. We have also the transition elements, and we have also the lanthanides and actinides. So if you look at the periodic table, you will have the representative elements, which are the main elements, group 1 and 2 and 3, 4, 5, 6, and 7. These are called the representative elements or the main group elements. Okay. Also group 8, they are called the rare gases or the noble gases. We have also the transition metals in blue in the middle. Okay. And we have also the groups lanthanides and actinides. And lanthanides and actinides are embedded into the periodic table between the elements 57 and 72 and 89 and 104. So actually, if you imagine the periodic table, it will be very long in width. That's why we take the lanthanides and actinides and we'll put them in the bottom. But you have to keep in mind that these elements are actually in between these they are occupying the space between these elements 57 and 67 and so on. Okay, so the representative elements and are also called main group elements. They have incompletely filled or s or p orbitals. That's something important. So they have some unfilled s or p orbitals. So for example, for lithium it has one s1, so it's unfilled. And they have also what we call the valence electrons, which they control their properties. The noble gases, they have usually filled electronic configuration, so they have full electronic configuration, usually like 1s2, 2p6 or something like that. The transition metals, what they are characterized about is they produce many cations. For example, chromium, it has chromium +3, +4, and +5, and so on. And what characterizes lanthanides and actinides is that they have F configuration. So that's those only ones that they have F configuration. Okay, and F of course can contain up to 14 electrons. Sorry. So now, what determines the chemical reactivity of elements is what we call the valence electrons. So when you do the electron configuration, I'm going to show you in 1 second what does that mean. You have something called core electrons and valence electrons, and the valence electrons are those who controls or specify the element property or chemical properties. Okay, and we found that elements with the same group actually they share the same number of valence electrons, So for example, for group 1, if you remember from last time, lithium, sodium, and potassium, they all share the S1 configuration. So they end up all of them with S1. So 1s1 or 2s1 or 3s1. For group 7, you will find that the halogens, you will find them to be having also the same number of valence electrons. So they have 7 valence electrons at the end. And I will show you that in a minute. So group 1, if you do the electronic configuration for them, like for lithium, it's 1s2 2s1. For sodium, you will also have it to be ended up with 3s1, and for the element underneath it's 4s1. So they all have s1 configuration. That's why they look all the same in their chemical properties. For the second group, they're s2. For the third group, for group number 3 or 3a, you will find it to be like something like 1s2 2p1, okay, and that applies to all the elements. They have the same electronic configuration at the end. It's just the end that is differs and so on. Now the problem with this classification is that this does not apply to all the groups, by the way. So the chemical properties, let's say for group A, 4A, which is the carbon, if you do the configuration for the carbon group, yes, you'll find it to end up with something like S2P2. But the fact of the matter is that these elements are not the same. So for example, predicting element properties based solely in group is not always accurate. So he's talking about the group 4A here, which ends up with NS2, NP2, but these are all not the same. If you look at carbon, carbon is non-metal. Well, silicon is a metalloid, it's something between metal and non-metal. And germanium is also a metalloid. But if you go down to tin and lead, which are down in the group, these people are actually metals. Because this is the periodic table again, and the periodic table, everything in blue here is metals, including tin and lead, which are actually under carbon. Carbon is non-metal. And everything in yellow here is non-metals. We can say that the group is noble gas. Actually, you cannot actually consider them non-metals. And things in purple, they're actually the metalloids. So if you focus your vision here at group 4A, the carbon group, this carbon group, they have the same electronic configuration, but this group contains metals, non-metals, and metalloids. Even the oxygen group actually contains a metal, which is polonium, PO. So the chemical properties of a group is governed by the valence electrons, but this is not a general rule here. So here is a question: an atom of a certain element has 15 electrons. Without consulting a periodic table, answer the following questions. What is the ground state electron configuration of this element? And how should this element be classified? And is this element diamagnetic or paramagnetic? Well, we can easily do the electronic configuration of this. But before I go actually to the electronic configuration, I just want to teach you a way to do the electronic configuration of elements even without memorizing this 1s2 to s2. You need to understand that this is the S area. Okay, this is S2 area. There's two groups here, and this is the D block in the middle. From here to there, D contains 10. So 1, 2, 3, 4, 5, 6, 7. Okay, and this is the P area here to the right. So if you want to do the electronic configuration for element just by looking at the periodic table, let's say, take example, carbon. So you say 1s2, okay, so this is 1s1, 1s2, then 2s2 here, and then 2p1, 2, so 1, 2p, 2p2. So again, if you want to do the carbon, you say 1s2, and then 2s2, and then 2p2. Let's try this again for another element. So let's say one is difficult, which is, let's say, chlorine. Again, 1s2 till helium, 2s2 till there, and then 2p6, they're all filled. I'm trying to get to chlorine. And then this is a 3, so 3s2, 3p5. 1, 2, 3, 4, 5. Till it comes. So this is how we do it without even memorizing the song. 1s2, 2s2, 2p6, 3s2, 3p5. You can try this again for, let's say, for titanium, Ti, which is 22. You can say titanium actually is 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, 3d2, because you are here in the 3d and you want to take 2 electrons from the d orbitals. Or simply you can say that titanium is actually argon, then 4s2, 3d2. So let's go back to the question here. He's talking about an element that has 15 electrons. So let's call this element X. We don't know what is it, 15. So this is 1s2, 2s2, 2p6. That's 10. 2 and 2 and 6 is 10. We need more. 1s2, 2s2, 2p6, 3s2, 3p3. So this is the element. 10 electrons, and yes. So now, guys, let's define what is core elements and valence electrons. The valence electrons, the definition of valence electrons, these are the electrons in the highest n, okay? They call them also outer electrons for representative elements. For representative elements, the valence electrons is the same as the outer. So here you have n equals 1, here you have n equals 2, and here you have n equals 3. And therefore, these are the valence electrons. So this guy has 5 valence electrons. Okay, the question is not asking about valence electrons, but just in case. So this is the electronic configuration. Now, this is A. Now, in B, in the question, in part B, he's asking, how does this element classifies? Well, this element has unfilled p orbital because the p contains 6 and there's only 3 there. So this is a representative element. Now, is this a metal, non-metal? We don't know. We cannot say actually if this is because as I told you, a valence electrons, the term is the group. So this is in group 5. Okay, this is in group 5. We know that because it has 5 electrons in the valence shell. But we don't know if this is metal or non-metal. We cannot determine it's metal or non-metal or a metalloid, because without looking at the periodic table, we cannot honestly tell if it is not or not. The last thing is that it's asking of this element is a paramagnetic or diamagnetic. Well, let's look at that. In the valence shell, we have 3s2, 3p3. 3s2, 3p3. So 3s2, that means you have paired electrons here, and you have 3p3. So clearly, according to Hund's rule, if you remember, you have 1, 2, 3. We have 3 unpaired electrons here, and this one is paramagnetic. So it responds to a magnet. If you bring this element, it will be attracted to a magnet. So this is paramagnetic element. This is the solution for this question. Now, after we solve this question, I advise you to solve the practice exercises after each question, as we always do, and just to see what elements we're talking about. 15 is phosphorus. Now we know phosphorus is non-metal, and it's also paramagnetic, okay, and it's group 5, as you see here. Now, let's move on to something about cations and anions, electronic configuration for cations and anions. Now, let's take a quick example, which is we always talk about. Let's talk about sodium, which has 11 electrons on it, and let's talk about fluorine, which has 9 electrons on it. Now, the electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1. So it is good. It's in group 1, so it finishes up with 3s1. So in this case, the valence electrons is 1 electron. Fluorine has 9, so it's 1s2, 2s2, 2p5. Okay. So these are both a representative element. The valence electrons for sodium is 1, so this is group 1. The valence electron for fluorine is 7, because if you're looking at the valence electrons, they are in the outer shell and the outer end here, which is 2, and then you have 7 electrons. Okay, so this is very important. So this guy has 1 valence shell electron, this one has 7 valence electrons. Now, if sodium likes to do an ion, he likes to lose this electron actually, because if you look at the periodic table, going back to sodium, this is sodium here to the left side of the periodic table. So in order for sodium, now there is a rule that says everyone wants to be a noble gas. Okay, if everybody likes to be perfect in the periodic table. Everybody wants to have a noble gas configuration. Now the closest two noble gases for sodium are, this is sodium, so the closest one is argon, but actually he can go back and so sodium has two solutions, either to lose an electron and become like neon, or gain 7 electrons and become like argon. So the first scenario is, of course, the one that makes sense. Sodium can make sodium plus ions. So this is ionization. If you remember, he can oxidize and lose an electron to become Na plus. And the electronic configuration for Na plus is 1s2, 2s2, 2p6. And if you look at this electronic configuration, this is the same as neon actually. For fluorine, let's go back to the table. Fluorine is right here to the left. And again, if fluorine likes to be to form ions, he has again two scenarios. The first one is to gain 1 electron and become like neon, or lose 7 electrons and become like helium, which is impossible, of course. This is too many electrons to lose. And so therefore that electron that the sodium formed or lost, fluorine can get that electron and make Na minus, sorry, F minus. And therefore the electronic configuration for fluorine is 1s2, 2s2, 2p6. And that's again an electron configuration for neon. So here we say that the electronic configuration of Na plus is the same as, actually the F minus is the same as Ne. They have all the same electronic configuration, and this is called isoelectronic. The word iso in English means the same, isoelectronic, and isoelectronic means they have the same number of electrons. Na plus does have the same number of electrons as F minus, as the same number of electrons in Ne. The only difference between these three people, by the way, is that they have the same number of protons. They have different number of protons. So sodium cation, F anion, and neon, they do have the same number of electrons, but they're actually different in the same number of protons, because we're not playing with the protons here. When sodium loses an electron, does not mean that we are playing with the protons. The protons and the neutrons are the same. Okay, and I think we've gone over this in chapter 3, I think. Okay, so we've did this. So now for group 2, they like to lose 2 electrons, and therefore for calcium, let's say, which has an electronic configuration with argon 4s2, he can lose 2 electrons and form Ca2 plus, and therefore it reaches an electron configuration similar to argon and so on. Now you can do the other stuff as well. By the way, this is called, when you do for sodium, when you write the full electron configuration 1s2 Na plus, 1s2 2s2 2p6, this is called the full electronic configuration for sodium. When you write sodium as Ne, that's called the condensed electronic configuration. So I'm going to explain this for another example here. Let's say that you want to do nitrogen. So nitrogen has 7 electrons on it in the base level. So it's 1s2, 2s2, 2p3. This is called full electronic configuration. Full electronic configuration. But if you look at the periodic table, you will find that 1s2 is helium. So this is helium. And then 2s2, 2p3. This is called condensed, like condensed milk, condensed electronic configuration. And the nice thing about the condensed electronic configuration is that you can tell the valence electrons right away. This has 5 valence electrons on it. Okay. So we usually write the condensed electronic configuration just to make it easy for us to write down, and also to know the valence electrons right away. Okay. So now we learned that group 1, they like to lose 1 electron, and therefore they make +1 ions. And I think I've been saying this since the beginning of the course. Group 2, they lose 2 electrons and they make +2. Group 3, they make +3. Group 4, which is the carbon, they make ±4, as we explained earlier. Group 7, they always make -1. Group 8, group 6, which is the oxygen, they make -2, but we remember that they also make other stuff. It says here that they make -3, but also group 5, they make ±3. So that's maybe this rule in this slide only applies to the first row of the second row of the representative elements, which is lithium and fluorine. But if you go down in the periodic table, you will find that elements, they make different cations. Now, what about the transition metals in the middle? As we said, transition metals, they make different ions. So you will have +2, +3, +4, and so on for the same element. Now, there is an important rule in the transition metals when you make an ion. It says this rule is first in, first out. You can write it down in your slides. First in, first out. That means when a cation is formed from an atom of a transition metal, electrons are always removed from the ns orbital and then from the n-1. So we take it from the s orbital first and then the orbital. Because remember, in the transition metal, when we fill the transition metals, we fill the force s, the s first, and then we fill the d. So first in, first out, that means we take, if you want to take electrons, you take it from the s, not from the d at the beginning. So let's take an example. Iron has an electronic configuration of argon 4s2 3d6. Now, if you want to make an ion out of iron, let's say you want to make Fe2+, then you take the electrons from the s first, not the d, because we fill the first n. It's first in, first out rule, and therefore the Fe2+ has 4s0 3d6, or simply argon 3d6. And in this case, you see here that we've taken the electrons out of the s orbital, not the d orbital. Now, if you want to make a higher ions, and iron does make a higher ion, which is Fe3+, in this case, you have no alternative but to take an electron from the d orbital. And in this case, it would become 4s0 3d5 or argon 3d5. That's why probably iron cannot, it's difficult for it to make Fe4+. Because if you want to take one more electron, you want to take it from a d5, which is half filled. And this is, I told you last time, this is very stable. Okay, a half-filled or a full-filled d orbital, a d5 and d10, is relatively stable, and therefore it's difficult to take electrons out of them. Okay, let's take another example, which is manganese. Manganese has a 4s2 3d5. Manganese can make FMN2 plus, and therefore, if you ask yourself where are these 2 plus coming out, are they going to take out from the S or the D? Then of course we take them from the S, because first in, first out, and the electronic configuration for manganese is 3d5. Now let's take one example here before we continue into the effective charge, just to practice this. Now, let's take a look at the zinc. Zinc has 30 electrons. You can make it, you can memorize the song to SS, PS, PS, DS, DS. Or you can just look at the periodic table to find the electronic configurations for zinc. And I'm going to do it again for you here. So zinc is 1s2 till helium, 2s2, 2p6, see that? 3s2, 3p6, 4s2, 3d, if you count this, it's going to be 10, 3d10. So zinc is filled. Okay, zinc is filled. Or simply, zinc is argon, four s2, 3d10. So again, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, because electrons, and argon has how many electrons in it? If you can look at, take a look at argon. Argon is 18. 18 and 2 is 20, so 30. 30 electrons in zinc. This is the correct electronic configuration for zinc, and this is called the ground electronic configuration. Ground state, okay? Ground state electronic configuration. This is ground state, means the normal state. Now, if zinc wants to make an ion, now the easiest thing for zinc is to lose these s2 orbitals. So zinc 2 plus is actually argon 4s2, 4s0, 3d10, which is simply argon 3d10. This is very stable, very nice electronic configuration. It has a noble gas configuration plus a filled d orbital. So that's why zinc can only make Zn2 plus. If you remember, even when we used to name zinc, when we say zinc chloride, which is ZnCl2, we don't say zinc 2 chloride, we just say zinc chloride, because zinc can only make 2 plus ions, and now we understand why it does make 2 plus ions, because if you want to make Zn plus 3 ions, you want to take electrons now from these d orbitals, which is difficult. Now I keep saying ground state and excited. What does that mean? Let's take one more example and I will tell you what is that. If I ask you what is the electronic configuration of carbon, which has 6 electrons, you say it's 1s2, 2s2, 2p4. So this one looks like that. So 1s2, 2s2, and then 2p4, 1, 2, 3, 4. This is called the ground state. Okay, ground state means the more stable, the lowest energy, the normal, the good electronic configuration. Now, sometimes what does happen, if you do something to this carbon, you excite the atom, or if you excite the atom by providing it with some energy. H and U means energy, according to chapter 7, sorry. H and U. Then this electron might jump or might move to another orbital. So this is 1s, this is 2s, this is 2p. The next empty orbital is 3s. So this electron actually might jump to a 3s orbital, and you might get into a configuration that might be look like this: 1s2, 2s2, 2p3, 3s1, which actually looks like this. Okay, this is different than this, of course, incorrect electronic configuration. If I ask you what is the electronic configuration for carbon, you're not going to do that. But this can be considered as an excited state of carbon, excited state, okay? So anything that is different than a ground state by having electrons in the outer and the higher subshells or shells, this is called excited states of atoms. You know this later. You can apply this, of course, to other elements. Okay. We're done with ions and cations. Now let's move on to electronic properties or to atomic properties of the periodic table. Now in this chapter we're going to talk about the size. We're going to talk also about the ionization energy, and we're going to talk also about the electron affinity. In order to understand these phenomena, we have to first discuss something called the effective nuclear charge, which we call Z effective. Okay, because this effective nuclear charge has actually a direct effect on the physical and the chemical properties of elements such as size and ionization energy. And before we start that, let's think about, for example, the size of the elements. If you look at the periodic table, and we have a copy of the periodic table right here, if I ask you about the size of the elements, you might guess that as you go down the periodic table, let's say for group 1, as you go down from lithium to sodium to potassium and so on, you think the size will increase because you're adding shells, you're adding more shells, n equals 1, 2, 3, and the size increases, and that's correct. The size does increase as you go down the group in the periodic table. But if you go from left to right in the periodic table, you think the size will increase because you're adding more electrons, but actually this is incorrect. Because in fact, as you go from left to right in the periodic table, okay, as you go from left to right and across the period, the size actually decreases. And this is a crazy idea, but it's a fact. So fluorine actually has a smaller size than lithium. And this is right. Fluorine does have a smaller size. And lithium, although it has more electrons. And the way we explain this is we explain it using the effective nuclear charge. Well, let's take these two guys here and explain what is effective nuclear charge. So we have lithium and we have fluorine. And I'm just saying that lithium, and I just said that fluorine is smaller than lithium. Now, why is that? Lithium has 3 electrons, fluorine has 9 electrons, okay? And you might say, okay, teacher, fluorine has more electrons, so it has a bigger size. No, it's not. Now look at this. Lithium has, now let's do it the old school way. You have 3 protons inside, okay? You have 2 electrons here, and you have 1 electron here. So you have 2 electrons in the first shell, in n equals 1. And you have 1 electrons in n equals 2. Now in the fluorine, you have 9 protons here in the middle, in the nucleus. You have 2 electrons in the first shell, and you have 7 here electrons. Now you have attraction forces between this nucleus and these electrons. So this nucleus actually in lithium, it's attracting these electrons as well as attracting this electron as well. And here as well, we have the same thing. So here we have a nucleus that is attracting 2 electrons and 7 attracting electrons. Now last time we defined something called shielding. In shielding, the 2 electrons in the lithium to the left are shielding 1 electron from coming up to the nucleus. So we have good shielding here. We have very strong shielding in the lithium. In the case of fluorine, we have 2 electrons, which are the core electrons, trying to shield 7 electrons from getting into the nucleus. But as you see here, these 7 electrons are just too big, so they're going to actually attract to the nucleus. They're going to win. Okay, they're going to cross the lines. They're going to, if you if you remember, they're going to cross the line and come up to and come close to the nucleus, and therefore here we have weak shielding in the case of fluorine, and that's why fluorine actually is smaller in size than lithium. I wish that you understand this point, and this is because of the shielding. Now you can actually do this in another way, which is the effective nuclear charge, called Z effective. So Z effective is equal to Z minus core electrons. This is the rule for Z effective. Okay? So let's do it for lithium and let's do it for fluorine. Now for lithium, Z is 3 minus 2 core electrons is 1. And for fluorine, it's 9 minus 2, which is the same. We have the same core electrons in both cases, which is 7. In this case, we say here that Z effective, the effective nuclear charge, Z effective in fluorine, it's much higher than lithium, and therefore fluorine has a smaller size, because if you have a nuclear charge that is really big and effective, it attracts electrons towards the nucleus in a much stronger way, and therefore you will lead to a smaller size. Nevertheless, as you go down in the group, in the periodic table, the size increases, but as you go from left to right in the periodic table, the size decreases, okay? Or simply, if you can here see my slides, I'm just going to draw it this way here. This is something you might do. The size actually in the periodic table increases this way. So the biggest element in the periodic table is francium actually, and the smallest element is fluorine, because the size goes, it goes big as you go down, and it goes big as you go to the left.